let us visualize this Clark's transformation. So, here I have shown 3 axes, okay, A, B, C, these are stationary axes, and let us first put this vector I A, space vector I A t, okay, which is basically rotating. So, as it is rotating, okay, as this is rotating at this position, if I see the time variation. So, at this position I A t, the maximum projection is happening on the A axis. So, the maximum projection is on the A axis, and on B and C axis we can see there is a negative projection, because you see this is the negative projection and this is the negative projection. Okay. So, for the B and C we may be here, okay, I B and I C same because of symmetry. So, this is the position. Now, as this vector I A t starts to rotate, what will happen? The projection on the A axis will start to reduce in magnitude. So, therefore, it will start to reduce in magnitude like this, and eventually when the vector is here, the projection becomes 0 on the A axis. So, on this diagram we are seeing with respect to time. Okay. So, we are I am an observer standing here, and I am seeing that, okay, as this vector is rotating, initially it had a maximum projection and then it is falling, becoming 0, and its 0 is happening at omega t equal to 90 degree. Okay. And similarly, then it will go minus when it will go like this, and then it will again come back 0 at this point here, and it will go like this, and this is a cosinusoidal variation. Okay. Now, so let us now see what happens for the B phase. So, when I A was here, of course, I told you that on the B phase the projection is negative. Okay. So, this was here. Now, slowly as the vector is rotating, at this point when the vector is here, when it comes here, then the projection becomes 0, projection becomes 0, right, and then after another 90 degree the projection becomes maximum. Okay. So, therefore, in total after 120 degree in time, okay, after 120 degree in time, the projection on the B phase will be, or the B axis will be maximum. We can do like this peak for the B phase will happen after 120 degree in time. So, will happen here, okay, and then it will follow like this. Okay. So, after 120 degree in time. So, this is 120 degree in time, okay, this is 0 degree, this is 90 degree, 120, and then this is, yeah, the scale has been a slightly, yeah, I have not drawn according to the scale. Anyway, you can understand what is the concept. So, this is 180 degree, and yeah. So, this is where the B phase projection will happen maximum, because after 120 degree the space vector becomes aligned to the B phase axis. In a similar way, the C phase also, it will get aligned to the C phase after. So, therefore, we can draw the time variation, okay, with respect to this space vector. As the space vector is rotating, we can draw the time variation. Now, let us see the alpha, beta and 0 axis. Okay. Now, the alpha, beta and 0 axis is another set of axis, okay, and this set of axis, this alpha, beta, 0 may be on the same plane, may not be on the same plane. So, first of all, let us see how this alpha, beta, 0 axis appear. So, this is shown actually by this diagram here. So, here we can draw a 3-dimensional surface here. Okay. So, this is a 3-dimensional surface or 3-dimensional plane in which you have the A, B and C lying on this. So, you have the A axis, you have the B axis and C axis on this plane. Okay. So, this is what is this plane here. This is the plane on which this A, B, C is there. Okay. Now, the alpha, beta, 0, this is another plane. So, let me draw it with another color. This is another plane. Okay. In this plane, you have the alpha axis, you have the beta axis and you have a 0 axis. The 0 is 90 degrees to this plane. So, this is the alpha, beta, 0 plane in a most general case. So, I am trying to visualize the whole thing. So, there are two planes, you can visualize it in this way, that this is the ABC axis in which A axis, B axis and C axis are on my hand here. Now, the alpha, beta, 0 plane is somewhere here, okay, and this plane is maybe at a certain angle to this one, to the ABC axis. In this alpha, beta plane, alpha axis and beta axis are on that plane, while the 0 axis is perpendicular to that plane. Okay. So, that is what I have drawn here. The alpha, beta is on the plane, whereas the 0 axis is perpendicular to that plane. This is the most general case. However, often there is no need for us to make two separate planes. So, what we do here is that we make the alpha, beta, 0 plane coincide with the ABC plane. So, this is the alpha, beta, 0 plane, we coincide with the ABC plane. So, which means that we will make it coincide. So, therefore, what I have shown here is that the ABC plane was this blue colored plane, and on which I can put the alpha beta plane. So, AB, this is the alpha beta plane with the 0 here, and the ABC plane is also at the same. So, ABC is here, A, B, C. So, ABC and alpha beta are at the same plane, while 0 is at the 90 degrees to this plane. Okay. So, this is what I have tried to show you, that they are at the same plane, alpha beta and ABC. Okay. In case the system is balanced, we see that in this ABC plane the space vector is rotating. Okay. The space vector, suppose IRT is rotating, because you have this A axis, you have B axis and C axis, and the space vector is rotating. In case of an unbalanced system, so in case of a balanced system, this is circular in nature. In case of an unbalanced system, then you have this A axis, B axis and C axis. However, this space vector is an ellipse, okay. But again that ellipse is on that plane, ABC plane. Now, in case of alpha beta 0, how do you see it in the alpha beta 0 domain? You see it like this way. So, you have the alpha, beta and the 0, and basically this is a 3-dimensional space vector. Okay. So, that space vector is basically rotating in a 3-dimensional alpha beta 0 with respect to the alpha beta 0 plane. Okay. So, here I can see that in the alpha beta 0 plane. Okay. So, you can imagine, so there is a, this is a 3-dimensional vector which is rotating in the alpha beta 0 domain. So, this is the alpha, the beta and this is the 0. So, you can imagine something like a box. Okay. So, you can imagine that there is a box kind of thing. So, you have the alpha, you have the beta and you have the 0, and one space vector is rotating in this box. Okay, 3-dimensional, it is rotating inside the box. So, that is the general alpha beta 0 when there is a 0 sequence component, but if there is no 0 sequence, if there is no 0 component, then this 3-dimensional elliptical orbit, that this reference vector, it no longer remains 3-dimensional, it becomes 2-dimensional. Okay. So, it becomes flat when there is no 0 sequence component. Otherwise, you can think of it as a 3-dimensional elliptical space vector which is rotating. Of course, this kind of visualization sometimes is useful, because if you can also do it through the mathematics, but sometimes this kind of visualization is important, because then you understand how the space vector is, where it is position is, like that. Okay. So, therefore, we see that in a general case this alpha beta 0 in that, so it is a 3-dimensional plane in which this vector is rotating. So, therefore, coming back to this diagram, I can say that this is the alpha beta axis which is on this plane, okay, which is on this plane, and then there is a 1 0 which is 90 degrees to this plane. Okay. And so, there is a vector which is rotating in this plane, and of course, you will then able to see the projection of this vector. So, this vector is rotating, and you can take the projection of this vector along the alpha axis or the beta axis or the 0 axis. So, therefore, you will have, so this is an unbalanced system. So, I am drawing 3 unbalanced waveforms. Okay. And this is what this is. This is the projection on the alpha axis with time, this is the projection on the beta axis, and maybe this is the projection on the 0 axis with respect to time. Okay. So, this we say that alpha beta 0 components. So, this we will term it as I alpha t, this we will term as I beta t, and this we will term at I 0 t with respect to time, okay, where the actual thing is rotating, actual space vector is rotating in the 3-dimensional plane. So, as I told you, in case of the balanced system, the 0 component in alpha beta 0 have 0 value. So, then what we do? We deliberately make the all these variables in one single plane. So, there is no 0 component. If there is no 0 current flowing, okay, when do we, either if it is a balanced system, there is no 0 current flowing, or if it is a system with an isolated neutral, or suppose it is a grid connected system, then I 0 cannot flow. Okay. So, we do not take care of the I 0, and so there is no need to represent I 0 in the system, and so we will draw it in this plane. Sometimes instead of drawing it this way, we also draw it like as if we are looking from the top. So, we say it like this is the A axis, looking from the top means looking from the top of this plane, we will see A axis here, B axis here, and C axis here, and we will also see the alpha axis here and beta axis here. Okay. The same thing, I am looking from the top, from the plane. Okay. This is what I will see, and of course, there is the vector. This was what I wanted to convey about the visualization. Okay. Yeah, all components remain in case of an unbalanced system, all these components will be present. Now, there is another form of Clark's transformation, and we have seen this form where we have seen this T c as 2/3 of this value, and T c inverse is this matrix here. So, this is called the magnitude invariant transformation. So, it keeps the magnitudes of variables same. However, another form of Clark's transformation is also possible, which keeps the power same, okay, in both ABC and alpha beta 0 variables. So, there we slightly change the multiplying factor and certain terms in the matrix. Okay. So, this is called the power invariant transformation. This is the power invariant transformation, but in this course we will not use the power invariant transformation, we will use the magnitude invariant transformation. However, in some book it is up to the discretion of the person who is using, he can take any of these forms of Clark's transformation. Let us now go into power. Okay. So, how do we define power? Now, the instantaneous power in ABC variables, we say that the instantaneous 3-phase power is VA times IA plus VB times, so VA times IA times VD times IB and VC times IC. Okay. So, this is nothing but VA IA plus VB IB plus VC IC. Okay. Now, what is the instantaneous power in alpha beta 0 variables? So, we can substitute whatever we have got. So, we can write this VA, VB, VC, this is also a matrix form. So, we write it like this way, transposed, and IABC as the same matrix which we have defined, and then we find that this is the expression of power in the alpha beta V0 variables. Okay. V alpha I alpha plus V beta I beta plus 2 times V0 I0 times this 3 by 2. Okay. The 3 by 2 factor is coming because the power should be irrespective of the reference frame chosen, whether you are in ABC or whether you are in alpha beta. So, that 3 by 2 is coming because of that. In the original definition we had a 2 by 3, and now this 3 by 2 comes because we want to keep the power same. So, that is one observation. The other observation is that this power is the multiplication of the voltage and the current on the alpha axis. So, V alpha t is the projection of the voltage space vector on the alpha axis time. So, V alpha into I alpha plus V beta into I beta plus 2 times V 0 into I 0. Okay. So, these 3 projections on the 3 axes and multiplying them together. This is the 3-phase instantaneous power. Okay. It is important, this is an instantaneous power. You see here T is there. Okay. These are all instantaneous quantities. So, it is the sum total of the 3-phase power at any instant of time, okay, in the alpha beta 0 variable. Of course, under balanced case the 0 components are 0. So, we do not need to actually, when we are dealing with power, we do not need to take care of that 0. Okay. Now, earlier we had talked about that there is a 0 sequence component or a 0 component in the space vector, but we had also talked when we had done the space vector PWM, if you remember, we said we had deliberately introduced a 0 component, okay, a common mode component in the 3 phases in the voltage. Okay. But that common mode voltage cannot inject a current because of the isolated neutral of the load or the grid, and that is why when we talk about power, we can neglect the contribution of this V 0 and I 0. V 0 is there, but I 0 is not there. So, therefore, that contribution becomes 0 and we can neglect it. So, the instantaneous 3-phase power then becomes P 3-phase. So, the V 0 I 0 goes away, although V 0 is present, but I 0 is not present. So, we can take it out. So, this is the equation. So, let us take an example, okay, and see how this P 3 phase T, what is the magnitude of it. Okay. So, let us consider a balanced system where you have this VAT as Vm sin omega t, Vbt as Vm sin omega t minus 2 pi by 3 and Vct as Vm sin omega t plus 2 pi by 3. Okay. Now, suppose let us assume that there is a capacitive load. Okay. Let us assume it is a capacitive load. So, therefore, the current will be leading the voltage. So, IAT is Im sin omega t plus phi. Okay. Similarly, you have IB as Im sin omega t minus 2 pi by 3 plus phi, and IC is Im sin omega t minus 4 pi by 3 plus phi, or I should have written it here omega t plus 2 pi by 3 plus phi, okay, just to make it sure like this is same as this one. Okay. Now, we can find out what is V alpha t and what is V beta t, substitute into the equation or in the matrix, then I see V alpha t is Vm sin omega t, and as expected Vm and Vm, they are matching, omega t and omega t matching, and A phase and alpha they are coincident. So, they have the same projection. V beta is minus Vm cos omega t. Why this is minus Vm cos omega t? Because this is alpha, this is beta, and at omega t equal to 0, the vector is here, right. So, the vector, so how is this equation telling us that this is the vector Vr at omega t equal to 0. Okay. That is why it is minus Vm cos omega t. At omega t equal to 90 degree, I will come here, Vr will come here, and I will have maximum projection on the alpha axis and 0 projection on the beta axis. Okay. So, this is like this. Okay. So, we can also similarly do for the current. So, I can find out I alpha t and I beta t. Okay. So, therefore, we can do the mathematics or put it into the matrix. I will get Im sin omega t plus phi minus Im cos omega t plus phi. Okay. So, then I go back to the equation of P 3 phase IT, which is this one, this equation, that is equation number 5, and I substitute there these values. What do I get? I get that P 3 phase T is, if you can do this yourself, put these values into the, substitute these values and solve it, you will see that P 3 phase is equal to 3 V RMS I RMS cos phi and is equal to the conventional power. In such a balanced system, we have V RMS I RMS cos phi, that is the power that is flowing into this capacitive load. Okay. And this P 3 phase T, this is an instantaneous quantity, but it is a constant value. Okay. V RMS is Vm by root 2 constant, I RMS is Im by root 2 constant, cos phi is constant. So, P 3 phase is a constant quantity.